Okay, let's dive into this. Welcome to The Explainer. Today we're tackling one of the absolute biggest computational challenges in modern AI right now, and that's making an AI actually understand long-form video. We're not talking about a quick 10-second clip here. We mean hours of continuous, dense visual data. It's just a massive, fascinating engineering puzzle. And, to truly grasp the scale of the bottleneck we're up against, we really need to look at the raw data payload these systems are forced to swallow. 60 million. Just let that sink in for a second. That's the exact number of tokens produced by just a single 1-hour 4K video shot at 24 frames per second once it's patched and embedded for a model to read. To put that staggering number into perspective, if you took a typical 2-hour spoken conversation and transcribed every single word of it, it would generate merely 30,000 tokens. So we're talking about literal orders of magnitude more data just to watch one single hour of high-definition video. This completely overwhelms your standard AI models, and it's forcing engineers to totally rethink how we process context. Here's our roadmap for today's explainer. First, the token explosion. Then, 4 paths to scale. Third, finding the needle. And finally, the production playbook. Section 1. The token explosion. Let's look at exactly how quickly video frames just absolutely devour a model's context window, and why those standard approaches break down so incredibly fast. Now, what's really interesting about this slide is how fast the math adds up. A single frame patched for a model like Qwen 2.5 VL natively takes up about 729 tokens. Even if you aggressively compress that using 3x3 pooling down to, say, 81 tokens per frame, a 30-minute clip at just 1 frame per second hits over 145,000 tokens. Now, that's doable for modern open models, but it's incredibly tight. But look at that bottom row. A full 2-hour movie at 1 frame per second demands over 583,000 tokens. That pushes us way beyond the capabilities of most open models, which means you need massive closed models like Gemini 2.5 Pro or some really extreme workarounds. Section 2. 4 paths to scale. So how do we actually solve this bottleneck? Because confronted with this sheer wall of data, human ingenuity kicks in. The engineering community has basically fractured into 4 distinct philosophical architectures to fight back. Let's look at each one. Path number 1 is brute context. The philosophy here? Pretty simple. Just throw immense hardware at the problem. You scale the language model's context window to millions of tokens and force it to process everything in one massive forward pass. Google really kicked off this era with Gemini 1.5 Pro, launching with a 1 million token context, and then Ultra pushed it all the way to an insane 10 million. Doing this requires serious engineering under the hood, like custom attention implementations with local, global, and sparse memory hierarchies, plus mixture of experts routing. It's incredibly powerful for sure, but as you might guess, it's highly compute-intensive and entirely closed source. The second path we're seeing is ring attention. Instead of relying on a single monolithic processor, you distribute the sequence. Imagine a circle of GPUs. Each device holds just a tiny chunk of the video's tokens. To compute attention across the whole video, each device passes its chunk to the next one in the ring, computing partial attention as the data rotates around. The LWM model used this exact method to train a 1 million token context, where the compute costs actually scale linearly rather than quadratically. Longvila also adapted this, achieving a 268,000 token context across 8-way parallelism. It's a super elegant way to distribute all that heavy lifting. Okay, moving to our third strategy, token compression. This is definitely cheaper than brute context because you're aggressively shrinking the sequence before the core LLM even looks at it. For example, Video XL takes a whole clip of multiple frames and crunches it all down into a single visual summary token. So at inference time, the LLM only sees these summary tokens, which drastically shrinks the required context window. Longvia uses a different trick, extending context via long context text transfer. Now, the crucial trade-off here is that you gain immense scalability, but you do sacrifice exact frame recall. The model gets the gist, but it might miss a split-second detail. But what if we don't have Google's massive server farms, and we still really need exact precision? Well, that brings us to our fourth path, agentic retrieval. The core idea here is pretty radical. Basically, stop trying to feed the full video to the language model. Instead, you treat the video file like a database. You use the LLM as an active agent to query that database for exactly what it needs. If we walk through the exact flow from the video agent paper, it works in 5 simple steps. First, the LLM reads your question. Second, it asks a retrieval tool to find relevant clips, like, hey, show me segments with a cat. Third, the tool scans the video and returns only the matching timestamps. Fourth, the LLM uses a vision language model to actually watch those specific short clips. And finally, it composes an answer. The real beauty here is that inference is incredibly cheap because the model only looks at a few seconds of video. However, it shifts the burden. Your system is literally only as good as its retrieval tool. If the tool misses the clip, well, the LLM fails.
And this brilliantly illustrates the philosophical divide in the industry right now. On one side, you've got the sheer force of brute context. It requires massive hardware, processes everything simultaneously, and is totally dominated by closed-source giants. The compute cost is sky-high, but the actual pipeline engineering is, well, relatively straightforward. But on the other side, agentic retrieval is highly efficient, open-source friendly, and boasts much lower compute costs. But the engineering? That's much harder because you have to build absolutely flawless retrieval pipelines.
Section 3, Finding the Needle. We have these 4 vastly different approaches, right? But how do we know which one actually works? That brings us to the ultimate battleground. Welcome to the needle-in-a-haystack, or NIH test. This is the absolute gold standard for long context evaluation. Basically, you take a massive video file, that's your haystack, and you digitally insert a unique visual or textual marker, the needle, at a completely random timestamp. Then you ask the model a highly specific question that requires it to recall that exact marker. This proves definitively whether a model actually understands the entire length of the video or if it kind of just skimmed the beginning and the end. When we look at the actual recall metrics here, the landscape becomes really clear. Gemini 2.5 Pro is just an absolute beast, scoring over 99% recall on videos up to 90 minutes long. And the earlier 1.5 paper documented 99.7% recall up to almost 9.5 million tokens. Closed models definitely dominate this middle ground. Meanwhile, open 72 billion parameter models perform admirably, hitting around 85 to 90% for 30-minute clips, but they severely degrade once you push them past that 60-minute mark. But here's the fascinating twist. When you stretch the video to 2 hours or more, Video Agent's retrieval approach can actually match or even beat the raw context models, provided its search tool accurately hits the needle. Section 4, the production playbook. Let's move to and see how this builds into what to deploy today. Because all this theory is great, but if you're an engineer tasked with actually building a video understanding pipeline today, what exactly are you supposed to deploy? Here's a super practical rubric. If your target is a 15-minute clip, you really don't need to overcomplicate things. An open 72 billion parameter model like Qwen 2.5 VL with its native context usually works perfectly for that. Now, if you're dealing with 30 to 60-minute videos, you've got a choice. You can go with long VLA or Video XL if you absolutely must stay open source, or just hand it off to Gemini 2.5 Pro if you need that top-tier, frontier level quality. But once you cross into 2+ hours of content, you really need to pivot to Video Agent or a similar agentic retrieval strategy. That's how you maintain reliability without burning immense amounts of compute. So the crucial point is that in the real world, production pipelines rarely just pick one single path. The emerging 2026 standard is actually a hybrid pattern. First, you run dynamic frame rate sampling and aggressive pooling on the entire video to compress it down to a much more manageable 100,000 token global representation. Second, you pass that compressed version to a vision language model to generate a comprehensive global summary. And finally, you use that summary as a structural index. Whenever a user asks a highly detailed question, the system uses that index to run agentic retrieval and pull only the exact clips it needs. It's awesome because you get the global understanding of brute context combined with the precision and efficiency of retrieval. As these architectures continue to blend and evolve, we're rapidly approaching an era of zero-loss, long-form visual understanding, which really leaves us with this final provocative thought. If we are building AI systems that can flawlessly watch and recall an entire lifetime of video data in mere seconds, what happens when the model remembers the needle better than the person who filmed the haystack? Thank you so much for joining this explainer, and keep exploring.